So, hello everybody. Welcome to the Sunday live stream. I know you've probably had a lovely weekend, hopefully, getting on a bit of your own work in your own time. This stream is, as normal, going to be split into two parts. The first half an hour, between about now and about 8 o'clock, if you're watching it live, is all aimed at GCSE, down on this side over here. And then from 8 o'clock, I'm going to be doing some stuff on A-level. So if you haven't already subscribed to me on YouTube, if you subscribe, it means you'll be notified if you want to turn on notifications. It also means that, like other people here, you can always obviously say hello in the chat and I'll try and answer your questions as the stream goes on. Now, I'm sure a lot of you are wondering what's happening this week in terms of resources. So what you can do is if you go to, there's a link again in the video description just underneath this. If you go to gcsephysicsonline.com and you go to the live page, you can see now everything that's coming up for the next few months. So there's all of May up and all of June. So basically, this is kind of my live streaming plan. By the way, hi Roxy, first person to say hi in the chat. Hope you're doing well. And Anissa as well. Great to have some sort of familiar faces back in the chat. You can select the date. So say, for example, you wanted to find out what's happening on the 1st of May. You just click on the 1st of May. It will kind of go down the page. And we can see that on Wednesday, for example, we're going to be looking at motors and microwaves. And then we're going to be looking at electricity and the uses of radiation on the 2nd, and so on. So basically, there's going to be a huge amount of stuff that's going on over the next sort of few weeks. And then what we do is we kind of have this big focus basically on looking at kind of paper one stuff and the things that you need to learn for your exams. So you can find the kind of schedule of what we're doing all over at gcsephysicsonline.com/live. And also, I believe when you go to that page, it does tell you about the fact that I do have these papers available that you can buy. This is a whole set of 12 practice papers specific to AQA triple science and the physics part of that course. 12 papers in total. And it's some of those questions I'm using in the live streams. So let's just begin. Now, the topic tonight is really looking at static electricity. So this is a topic which tends only to be covered by those doing triple science, which I know is a lot of you people out there watching. So if you're doing combined trilogy, this might not be the best thing for you, but of course you know what's in the specification and you know the topics coming up. So let's begin. So when a polythene rod is rubbed with a cloth, the rod becomes negatively charged, and that's basically charging by friction. And then we just need to complete this thing here. So again, there are going to be 3 words that we need to put in here. So if you want to, that's Katsuri, Nathan, Musky, Roxy, Anissa. Some of your names, they're so hard to say with the kind of the names you've got on YouTube. So what's the first word, the second and the third? So the rod becomes negatively charged because something are transferred from the something to the something. Okay, I suspect even if you haven't been taught this recently, a lot of this is kind of like a logical thing. So we know about the polythene rod being rubbed, it becomes negatively charged. Yeah, the first one is electrons. I'm going to go into green tonight, so I'm just going to write in green. So the rod becomes negatively charged because the electrons are transferred from the something to the something. So if we have things which are negative, the negative particles that we know about are electrons. Okay, they have a charge of -1 if we look at their relative charge, and also it's actually a very, very small number of coulombs. It's about 1.6 times 10 to the minus 19 coulombs. So the actual charge, if we measure it in coulombs on each electron, is really, really small. And that's because they're transferred from the cloth to the rod, and the rod becomes negatively charged. So that means the electrons must end up on the rod. So they're being transferred from the cloth to the rod. Okay, so effectively, the way we can think about this is we have an atom. We've got the kind of the positive dense nucleus here. We've got the electrons which are orbiting it in their kind of specific shells around the outside. And what we do when we're charging by friction is we're effectively taking electrons off this. So if we remove an electron and then we transfer that somewhere else, we're now left with something which has more positive charges than negative charges, and that means this whole thing here would have a positive charge and something else would have a negative charge. So again, think back to how this is related to ions when you're doing GCSE chemistry, things like ionic bonding and all that kind of good stuff. Basically what we're doing is we're taking these negative particles, we're putting them somewhere else, we're storing them there, and that means we probably have an insulator that kind of stores them so they can't really flow away, and that means we've got an overall negative charge there, an overall positive charge somewhere else, and because the charges aren't moving, we call this static electricity. Mustang, thanks so much. Right, we then have a student tries to charge a copper rod by friction. The student holds the copper rod in their bare hand and rubs it with a cloth. They find that they are unable to charge the copper rod in this way. Suggest why that is. So what we have here is polythene, and you could have any kind of plastic. It could be, well, I'm sure there's loads that you could have. Often acrylic is used. A polythene is going to be an insulator. Okay, and the cloth is also an insulator. So when we have this kind of charging by friction, it's often when we have two insulators rubbing against each other. The copper, however, is going to be an electrical conductor. And it's an electrical conductor because we have these free electrons. So Anissa has said copper is a conductor of electricity, so cannot build up static charge as well. Yep, that's good. So, so I think the first thing we want to do is realise that there's a couple of marks available, so we need to have a couple of points. And don't forget it is only GCSE physics, and that means lots of the answers are actually going to be relatively straightforward, and it's almost like stating the obvious. So as Anissa just says in the chat there, copper is a conductor. And then you could say that, you could then say that, so the electrons can flow along the rod to the person holding it. And it is earthed. So effectively, just kind of my small diagram here. Here's that copper rod. As you're charging it, we might be rubbing off some electrons, maybe from that cloth, and the electrons kind of end up on this. So it starts to gain a bit of a negative charge. But then if you've got somebody over here who's actually holding onto it, so they're holding onto that, the electrons can move through the material. We're still able to conduct things, so the electrons move through us down to Earth, and that means this still has a neutral charge. Okay, so yeah, static electricity. What date is the physics exam? Off the top of my head, I can't remember, but I think you've got 22nd of May. Okay, so you've still got 3 or 4 weeks. How many days is that? How many days do we have until your GCSE physics paper 1? Yeah, right. 22, I think. 40. Yeah. So, yeah, and also 14th of June is paper 2. So that is like, that's so far away. I mean, we're only in April. That's like a month and a half away, and you can do a lot in that time. Okay, so what we're talking about here is keywords. I'm just going to underline these. We've got the fact that copper is a conductor, and that means the electrons can basically flow along the rod to the person holding it, and it's earthed. So kind of some of these kind of key scientific words are things that you will be familiar with, and if you've been reading through the specification, if you've been making your own flashcards with kind of key terms on it, these are things you're going to be familiar with. Right. Now, the next thing here is we have a Van de Graaff generator, and charging by friction occurs when what we have is inside this we have a rubber belt. So this is a belt that kind of moves around. It's made out of rubber, and of course rubber is an insulator. Okay, and actually what it does is it rolls over a polythene kind of rod that's kind of in the top. So there's basically like a kind of like often a cylindrical piece of polythene. So there we go, we've got like a polythene thing at the top, and what we have again is this charging by friction, and the motor at the bottom, all that's doing is causing this belt to move up one side and down the other. So that's all the Van de Graaff generator is. Now, we're saying that the dome is approximately spherical, which is kind of what you've seen. By the way, if people in the chat, have you all seen this in school and have you touched it? Have you had an electric shock or have you been a bit too scared? Because I know that some of these, they can be pretty sparky and quite a lot of fun. So it'd be great to know in the chat if you've actually had a go with one of these. Now, that question there, yes, good. People are using it, yes. Okay, this is good. People's hair, Tanisha, hair stood up. Awesome stuff, Mustang. Yeah, ML, Anissa. Yeah, people shocking people. They're not banned over safety. Somebody at Spark My Friend's hand with it as well. They're not banned, but they have to be used carefully. So they can be used, but obviously not with people who've got a known heart condition. And also, you shouldn't be linking hands around the class, although it's really good fun, because you can actually build up quite a lot of charge on lots of people. But I know it's something that is definitely quite memorable. Right, so the question says, complete the diagram to show the pattern of the electric field produced by the dome, assuming that the dome becomes positively charged. So my thing here is that the dome becomes positively charged, okay? So I'm going to add some information to my diagram because this is going to help me answer it. So stuff in the question that could be useful, add it onto your diagram. So I'm going to put a big plus there. Now, the shape of that electric field is going to basically radiate away from this. For all of you who've had a go and actually maybe seen Mr. Bean as well, you know that if you put your hand over here, nothing happens. When you bring your finger a bit closer, you maybe feel the hairs on your arm maybe start to like stand up. And it's only really when you touch it or almost touch it that you get that spark. And that's because the electric field is going to be strongest closer to this. Now, a lot of you are probably quite familiar with drawing in magnetic field lines, maybe the lines around a bar magnet or through a solenoid. Well, we can represent the electric field in the same way by drawing field lines. And where the field lines are closer together is where we have a stronger field. And at the moment, this is kind of GCSE / IGCSE. I think this topic comes up in IGCSE as well. So this is basically just physics for everybody. So the way I'm going to do this is I would say use a ruler. And what I'm going to do is draw a line in pencil, okay? And this means if I make a mistake, I could actually rub it out. But of course, I know what I'm doing. I'm an expert at these things. And therefore, I'm just going to go straight to the pen to show what we have. So I'm going to do a line like that. I'm going to do another line that meets the surface and then it stops. And I've got another one on this side. And I'm going to do another line. So again, going away from the surface like this, and another one that looks like that. Okay, so these are the field lines, but that is not enough to get the marks. Okay, the other thing we need to have is we need to have an arrow that goes on the field lines. Okay, that one there wasn't the neatest. That's probably why pencil's a good idea to begin with. So what I've done is I have drawn the following things. I have drawn 8 lines. I've used a ruler. Okay, we have an arrow to show the direction of that electric field. And the other thing is, if you look at it, all of these lines meet the surface at 90 degrees. Okay, so what we do here is we basically draw a line at 90 degrees to the surface. And if you do all of that, then you're guaranteed to get 3 marks. Okay, good question from Zuxi. Would the arrows be switched if the dome was negative? Yes, they would. Now, the way that we draw electric field lines is basically electric field lines go from positive to negative. So what we can see here is we have something positive, so all the field lines go away from the positive dome. If this was negative, we'd have all the field lines going towards the negative thing. So electric field lines go from positive to negative, just I suppose a bit like how magnetic field lines go from north to south. Okay, and effectively, if you're not sure about which way they should go, you've got to think about if you had a positive charge. So I just happen to have one of my alpha particles here made out of Lego. So we've got a couple of positive protons. If you put a proton, if you put maybe an alpha particle, which has got 2 protons, so it's got a charge of +2, if you put that near the Van de Graaff, it would be repelled from the positive charge here, and the 2 things would move away. Now, if you put it here, it's going to move away like this. If you put it over here, it's going to move away this way. If you put it near the bottom, it's going to move down. If you put it to the side, it's going to move in this direction over here. So you've got to think about, with these electric field lines, which direction would a positive charge move in that electric field? And the other thing here that I think it's important to note is that the field lines, look, they're closer together near the surface, and as you go further away, the field lines get further apart. Okay, so I think we've done enough on that bit so far. Now, the next thing, again, I know a lot of you have had a go on the Van de Graaff at school, which is amazing. There's something here where what happens when a light aluminium foil cupcake case is placed on the Van de Graaff generator dome. So this shows what happens, and the dome is positively charged. The foil case flies up off the top of the dome. So has anybody seen this in school, where you basically get a stack of these foil cupcake cases, you put them on top of the Van de Graaff, and they all start flying upwards? So, has anybody seen that? If so, that'd be amazing. I think I've got it in one of my videos. I think people might have seen the electrostatic video I did, where we had like Barbie's hair stood up on end. Yes, a few people have seen that. So, this is a really nice demo. I'm afraid I don't actually have a clip of it to show within the live, but I do know I've got clips of it at GCSE Physics Online. It didn't work in your school, Tanisha. Yeah, sometimes that happens. Ideal. Is this for triple? Yeah, this is very much like a kind of triple science kind of topic. I think it's only those doing triple science who need to know about static electricity. However, you can still watch it. You can still gain some bits of GCSE knowledge. Just have it in the background while you're doing some other work. So, what's going to happen? The dome becomes positively charged. I'm just going to put a plus there to show that's positive. Now, if it's placed directly on it, then just as much as that's going to get positive, this is going to get a positive charge as well. And what we then have, as Zeno said, because both the aluminium foil and the dome are positively charged, so they repel. I reckon that is a perfect 2-mark answer. So what we can say here, actually, I'm just going to write down what Zeno said. We can basically say that both the metal foil case and dome become positively charged, so they repel each other. Okay, I think that's pretty much it, really. And of course, when that electrostatic force is going to be big enough, although, and maybe let's just think about the forces acting on this cupcake case, there will be a force down due to the weight, and that's the thing that's holding it down. But there's going to be a point where the electrostatic force is going to be bigger than the weight. And if this electrostatic force is bigger than the weight, that means there's going to be a resultant force upwards, and it's going to fly upwards. Okay, there we go. Right, describe how the strength of the electrostatic force between the aluminium cupcake case and the dome varies as the distance between the case and the dome increases. So basically, initially, that's really close. And as we saw in the previous question, we have a stronger field nearer to that dome. Okay, so ML says, as the distance increases, the strength of the electrostatic force decreases as the field lines are becoming further apart. That is an excellent answer. So what we could say, and I think that's the first bit of the answer. So I'm going to say that, and this is ML's answer, so a brilliant one there. And again, this is all good practice. If you type it in the chat, then it doesn't matter if you get it wrong, because you can always just like retract the message. I know other people have retracted messages when they get it wrong, but if it's wrong, it doesn't matter. Nobody cares. Okay, so, but it's good practice to kind of type it out. So as the distance increases, the strength of the field decreases. And we can say, for example, as the field lines get further apart. And this then means that the force, so how the strength of the electrostatic force, so the strength of the field decreases, and therefore the force decreases. Okay, and I think that's pretty much it for 2 marks. So that question there, actually, again, although it's a question about electric field strength, we need to maybe still consider what happens in terms of the forces acting on an object, and also, like, the shape of the field around these charged objects. Now, for the last sort of 10 minutes or so, I thought I'd go through some other questions. Now, these questions are based on one of the worksheets that I've done for GCSE physics, and let me just show you what I've actually produced over the last sort of few years. And I really kind of started these in lockdown, so I had my own source of questions. Now, if you go to my GCSEphysicsonline.com website, I'm sure you've been there by now. I'd say that probably about 60 or 70% of the website is completely free for you to view, but there are extra videos that are behind a paywall, and it doesn't cost much, but it gives you access to everything. Alex says, would you lose marks if saying the force was weakened rather than decreases? I reckon at GCSE they would give you the marks for there would be a weaker force. Yeah, I think, yeah, the force is weaker because it decreases. But I think, Alex, you would get the marks for that because it's clear that you know what you're talking about. Right, at the very bottom in the footer, where I can have links to quite a few things, I do have a link here to worksheets. So there's some equation sheets, there's stuff with Isaac Physics. If you click on worksheets, there's a list of all of these worksheets that I've got for GCSE physics. So maybe while you're revising, you're doing some of your past papers or my practice papers, you find there's a topic you're not so confident about with, what you can do is you can go here, you can see a list of all the worksheets I've got. The one we're doing today is static electricity. And basically if you click on that, if you haven't already become, oh, this isn't such a good demo. If you haven't actually got a premium plan yet, you can obviously buy one and then you can access this sheet. And it also comes with, of course, work solutions and video explanations as well. So I don't just give you questions, I give you nice work solutions and I have videos as well. So let's just do this quickly, shall we? Right. Everybody, question number 1 in the chat. What is the relative charge of an electron? So let's see what people say. It doesn't matter if you're wrong, let's just see what people say. So what is the charge on an electron? ML is first saying -1. Zeno -1, Katsuri, Nathan, Anissa. Yeah, great. Everybody there is saying -1. Okay, that's a relative. Hello, Bramble. I used to have a cat called Bramble. Alex, Sophia, yeah, -1 because an electron is negatively charged and the relative charge is -1. Okay, right, let's think about another. Okay, right, let's do number 4 next. Complete the following. Like charges something, opposite charges something. Oh, people ask what happened to the cat. Well, I had the cat when I was younger, so this was like over 20 years ago. So, yeah, I'm afraid 20 years is a long time for a cat. Right, number 4. Complete the following. Like charges something, opposite charges something. So we've got Anissa in, we've got Katsuri, loads of people there. Zeno, ML, yeah, so basically like charges repel and opposite charges attract. Okay, just like 2 opposite poles of a magnet attract, equal poles of a magnet repel. Okay, great stuff over here. Right, if one insulator gains electrons and the other loses them, write down if the 2 insulators attract or repel one another. So, number 5, if one insulator gains electrons and the other loses them, write down if the 2 insulators attract or repel each other. Okay, it's all right, Hirsch. I know at the moment on a Sunday night there's only 22, but I know lots of people are going to join for A-level, and I know that I'm doing this for the next month or so, so we'll see how many people join in, especially just beforehand. People are saying attract, and that is completely right. So effectively, if we've got this kind of insulator, and basically what we do, we rub it up and down next to this insulator, then some of the electrons are going to go from here onto this one, and that means this thing will become negatively charged and this will have a positive charge, and then the two things are going to be attracted to one another because they now have opposite charges. Okay, write down what surrounds every charged particle and how it might be displayed in a diagram. So this one's a little bit more tricky. So number 6, what surrounds every charged particle and how might you display this or show this in a diagram? So around every charged particle, what do we have? ML, an electric field displayed with lines that point away or towards it. So every charged particle, so we might think about a single electron or maybe a single proton. Okay, around these charged particles, there will be an electric field. And the field, if we think about the lines, these point from like the positive to the negative. So imagine if we just had an electron and a proton, the field would actually look a bit like this. Okay, and it's displayed with lines which have arrows, and the arrows go from positive to negative, as we said for number 7. Okay, number 8. Let's see how much people can remember. What does it mean if the electric field lines are closer together? So, what does it mean where the field lines are closer together? Again, we've already kind of talked about this, but again, it's good just to kind of remind yourself of what we've done so far. Okay, it's stronger. Yes. People are saying they are stronger. Stronger electrostatic force. The force is stronger. Great stuff, everybody. So if the field lines are closer together, just like with a magnetic field, that's where we have that stronger field. Bramble, good stuff. Nice. Okay. Right, a circular balloon is rubbed with a woolly jumper. Draw the electric field lines around the balloon below. So my first question is, how many field lines should I draw? If you were going to answer a question like this in an exam, how many field lines would you actually draw around this to kind of make sure that you get all the marks? 6, 8, 8. ML says 8. Anissa says 8. I reckon you are correct. I reckon you want to go for at least 8. Okay. The reason is it's easier to draw 8 than it is to draw 6 because you can basically just get your ruler. Again, you should be doing this in pencil. Okay, so use your ruler. You draw the field lines up to the surface. They're all actually at 90 degrees to that surface. So they're normal to the surface. Bramble, great stuff. So we've got 8 field lines there. And because we have a positive charge, the arrows point outwards, which is correct, Anissa. Very good. So we're going to draw an arrow outwards pointing away. And that's basically an easy 3 marks if something like that happens. So they should be pointing outwards away from the positive charge. Again, imagine if you had an alpha particle, which is positive, where if you put it in the field, which way is it going to go? Well, it's going to be repelled from the positive thing and it's going to move out in this direction. Okay, a teacher rubs an inflated balloon on their head. The hair on the teacher's head loses electrons and the balloon gains them. So, write down which insulator is positively charged and which is negative. So it says the hair on the teacher's head loses electrons and the balloon gains them. So if the balloon is gaining electrons, that's going to become negative, and the head is going to become, or the hair is going to be positive. Right. Now, people have said that already. Hair is positively charged. That's excellent. Why do the hairs stand on end? So why is it? I found the perfect Lego piece to show this. Basically, what we have is we have a hair. So imagine you've got some hair like this, okay? Now, all of these hairs are going to have a positive charge on them. And that means each hair is going to repel the hair next to it. And so because we have all of these positive charges next to each other, that then means that each hair wants to get as far away from the other hair next to it, because all the positive things are repelling all the other positive things, because like charges repel, and that's why your hair stands up. Okay, I reckon we'll leave it there. And Zeno said, yeah, hair repels each other as they're all positive, and also ML says that they're going to be attracted to the balloon. So you can see here, again, my Lego balloon and my Lego hair, this kind of, although the hair's sticking up, it's also kind of aimed towards that negative thing. Do I ever get bored doing GCSE physics, Tanish? I do, but that's fine because now it's going to be time for the A-level stream. So a nice segue. So thank you so much for the GCSE crowd. You are part of the elite. You're the people who I know are going to be doing really, really well because you've still got a month to go, and a lot of the answers I've seen have been really, really good. But I do like GCSE. I like A-level more. I think just because, although I do like GCSE and it does cover the basics, I think A-level is where you get some really, really interesting topics and really interesting maths as well, where we sort of put it into practice. So, bye everybody. When am I next doing a stream? I'm going to be doing a stream tomorrow, which is Monday, and then Tuesday and Wednesday and Thursday. Okay, so this is the first of my streams this week. I'm going to be doing another 4 each evening at 7:30. But of course, now I guess the A-level lot are coming out. And what I need to show you first of all is what we're going to be doing this week. So let me just sort out my iPad. Right. So this is my plan for this week. For the live streams, I've updated basically for the rest of this week. So if we look around down to the 28th, today we're going to be doing some stuff on simple harmonic motion and a practical. So again, kind of the skills you might need for like paper 3A if you're doing AQA. We then have a force equals BIL practical tomorrow. We're going to be doing resistivity on Tuesday. And this is a question from one of my practice papers for paper 3A. And then we've got some 2 different sorts of practical about measuring the Planck constant. So again, this is like great for anybody doing AS physics who has their real exam soon, and also for anybody out there who needs to be revising the year 12 stuff. Now, the other thing is that what I'm doing is, I'm sure you might have seen this as well, is that on my GCSE and A-level physics channel, which is Physics Online on YouTube, on the community tab, I'm doing multiple choice questions every day. So it'd be great to know for anybody watching this if you've actually done any of these so much, if anybody's actually had a go at these so far. You can see, for example, that the one that went out this morning has had like 700 GCSE people answer it. Yesterday, about 1,100 people answered this A-level question. And you can see that there's a whole load of questions, just simple things for you to have a go at each week. Jacob says that you've done a few. Excellent. Yeah, I think quite a lot of people probably watching this have had a go at some of these already. I did put up a poll just a few minutes ago, which is something I'm thinking about doing, which is basically a 3-hour kind of, I guess, cramming session, maybe on the weekend or in the half term before your final exam. And this would be specific to an exam board. So I do like a 3-hour AQA A-level session for paper 1 or for paper 2 or something like that. So I'm just going to look at how many people have actually answered that. So today, I put up this thing just before, and it says, okay, 41 minutes ago. I put up a question saying, anybody interested in like a morning revision session, limited places available. I think 40% of the people so far are interested in AQA A-level, OCR quite popular, less people interested in Edexcel, and I think about 1% interested in AQA GCSE. So potentially then I reckon AQA could be a goer, OCR probably, Edexcel I'm not sure, it depends on how the numbers go, but maybe not GCSE. So I might just be doing, for all of you people watching this, some A-level morning sessions, maybe 2 or 3 hours in the morning on the weekend before your exam. If you'd like me to do that, then do let me know. And I'd probably be running these on Zoom, a bit like a kind of big kind of tutorial, so there'd be less people. It'd be easier to answer questions. I could obviously send you out work beforehand. So if anybody would like that, then do let me know in the chat, and obviously I'll respond to what people are wanting. Okay then, let's do some physics, shall we? So this question here is, again, one of my questions from my daily workout book. If you're year 13, it's probably a little bit late to buy the book now because you need to be like, you know, straight into like practice papers. But this question comes from the 13th of September. And what I did really is I had questions that sort of built up to this previously. So we're looking at radians, we're looking at some differentiation, we're looking at some of these things about like frequency, angular speed. And then we've got this question here where we have an SHM, so simple harmonic motion. We have an oscillating spring system, but it's going side to side. whereas often we have things that tend to go up and down. So we're going to be doing this question here, and then you can see how as time goes on there's more questions related to this, and actually you can see why, especially if you're in year 13 now, why I asked you to differentiate these different things. We've got different sorts of graphs, and that's all good stuff. So basically this kind of stuff happens, and it kind of builds and builds and builds. Now the question says, a wooden trolley is connected to 2 identical springs which are attached to 2 retort stands held firmly in place as shown above. So we have this trolley here, we have 2 springs, and it's displaced to the right by displacement x as shown below. So that's like the central point, and basically the trolley is moved to the right. Now most of the time, and I still don't know the reason why we do this, is we say that s is going to be displacement. Okay, so that's kind of the way that we always do things, you know, think about SUVAT and so on. But when it comes to looking at things maybe like waves or things that oscillate with simple harmonic motion, we then use x to represent the displacement. And I haven't really found a satisfactory reason why that is, but that's just what it is. At the instant the trolley is released, state the direction of the resultant force on it. So, in the chat, if you want to, if you haven't already subscribed, make sure you do on YouTube. Which way, if we release the trolley, state the direction of the resultant force on that trolley. So, is it left or is it to the right? Let's see what people think in the chat. And by the way, looking at the chat so far, somebody says I'm a legend. Thank you very much. Yes, please, to these revision sessions on the morning or the weekend near the exams. It'd be great if I could, says Jamie. That's fantastic. Please, says Moodle MIP in capital letters. I think maybe they're wanting Edexcel, so that's a possibility. So which way does this go? Does it go to the left or the right? Well, if we're displacing it to the right, we can see that actually this spring here is extended and this one's kind of compressed a bit. So that means the resultant force is going to be Anno, Jamie, the birds, Moodle saying to the left. So the answer is the force is to the left. State the direction that the trolley would then initially accelerate in. So if the resultant force is to the left, so the force is in this direction, which way is the acceleration going to be? Well, again, this is now using Newton's second law, talking about how the force is proportional to the rate of change of So Newton's second law, force is going to be proportional to the rate of change of velocity. So yeah, to the left. So because F equals ma and the force, I just really messed up saying Newton's second law there. Okay, F equals ma. Now the force is to the left, and that means the acceleration is going to be to the left as well. So what we have is the displacement is to the right, but the acceleration is to the left. And therefore, we can say that the acceleration is going to be proportional to minus x. Okay, which is obviously then the kind of, that comes into the whole simple harmonic motion thing. So as a positive displacement from the central point decreases, describe how the acceleration of the trolley changes. So basically, when you go further to the right, we have a bigger value of displacement. We're going to have a bigger tension in this spring, and therefore there's going to be a bigger force pulling it to the left. So the bigger the displacement, the bigger the force, and the bigger the acceleration. When the displacement is only small, we're going to have a smaller resultant force, and therefore a smaller acceleration. So what we can say then is that describe how the acceleration of the trolley changes as a displacement from the central point decreases. We can also say that the acceleration decreases. Okay, and then once the trolley moves to the left of its initial rest position, state the direction of the acceleration. So now we have a negative value of displacement, okay, and that's going to be now to the left, but the acceleration is going to be to the right. And therefore we'd say that that has a positive acceleration. If we're saying that anything to the right is positive, anything to the left is negative. So this really shows what we have when we have simple harmonic motion. The acceleration is going to depend on the displacement from its rest position, and it's going to be the negative value of it. So positive displacement, negative acceleration, negative displacement, positive acceleration to the right. And that's just what we have with the simple harmonic system. Okay, so that one there is just kind of like logically thinking through things step by step. And I reckon if you're in year 12, you could basically teach a lot of this to yourself, because some of it is kind of fairly obvious. Okay, right, now, when the trolley is pulled to the right and about to be released, describe how the energy of the system is stored and state the equation used to calculate this. So, at this particular point over here, we've pulled it to the right, but we haven't released it yet. So what store is the energy stored in? So let's see what people say in the chat. The ones that we tend to think about are kinetic energy. We talk about gravitational potential energy. We talk about thermal. We might also talk about elastic. And I'm going to put EPE, or elastic potential energy. So yeah, basically it's stored in the elastic store. So that's elastic potential energy. And what's the equation that we use to calculate that? I suppose it's not so easy to do that. The reason it's not kinetic energy, Jacob, is because we don't have anything moving. So this is still static, and it's not moving at this time. Okay. Also, there will be energy in the gravitational store just because this is on the table, but effectively the change in gravitational potential energy is 0 because we have a horizontal SHM system rather than something going up and down. So Blah says that this is equal to a half kx squared. You could also say it's equal to a half k e squared, or you could say it's equal to a half k delta L squared. Oh, I've gone on to my paper just beyond it. So really, the extension, or indeed the compression of a spring, the extension is either an x, an e, or a delta L. It just really depends on which exam board you're doing. But of course, we could also, as Bramwell said, extension is a half FL or half FX. Yeah, perfect. Lucy, great stuff. Rithi, yeah. So lots of good answers there. Right. State the value of the displacement when the kinetic energy of the trolley is at a maximum value. So basically, we pull it to the right and we let it go. When will that have the greatest kinetic energy? So when will that trolley be travelling fastest in its journey in terms... Yeah, so state the value of the displacement when the kinetic energy is at its maximum value. So what we're looking at is Ke max, and we know that's going to be equal to a half times m times v max squared. So the question then really is, where is v max? And as loads of people are saying, we've got Anno, Jamie, Moodle, Jacob, Lucy. This is when x is equal to 0. So actually, when x is equal to 0, that's when the velocity is its maximum value. And also, because we know, as we saw over here, the acceleration is proportional to the displacement, at the middle point, it's not actually accelerating to the left or the right. It's still moving, it's just not accelerating. And so here, we can also say that the acceleration is equal to 0. Okay, of course, when you have the maximum value of displacement, that's when the value of the velocity is going to be 0, because when you've got the maximum displacement, it's not moving as it's changing direction. And also, this is where we're going to have our maximum value of acceleration, but it's going to be in the opposite direction to the displacement. Okay, so yeah, that one there, all steady so far. We now have, it says here, once the trolley is released, it oscillates about the central rest position. So you release the trolley, and it just goes left and right and left and right. We then have a graph showing how the energy is related to the displacement of the trolley. The total energy of the system, ET, is given with this dotted line over here. And this is obviously assuming there's no losses to the surroundings due to friction and air resistance. And the kinetic energy has been plotted. Sketch a line to show how the energy described in part E changes with respect to displacement. So this is, I guess, one that you can't really quite easily add into the chat. But I would say that what we need to think about is the kinetic energy, EK, plus, I'm going to call this elastic potential energy, EE, okay, plus the elastic potential energy is equal to the total energy of that system. Okay, now of course, it says here that the maximum kinetic energy is going to be where the value of x is 0, and when x is 0, it's in its equilibrium position, so that's where it's going to have the minimum value of elastic potential energy. And as Lucy says, the graph is opposite to the one drawn. So here's our displacement, and the bit in the middle is going to be 0. Okay. Now, for the sake of this, just to try and make it seem easier, imagine that we pulled it to the right, maybe 5 centimeters, or let's say we pulled it about 6.8 centimeters to the right. Okay. Now, what we could then say is okay, maybe that's 2 centimeters or 0.02 meters. We've got 0.04 meters, 0.06 meters, 0.08 meters. So that's the distance that we've pulled it to the right. And we'd have the same over here. So we'd have minus 0.02. We then have minus 0.04, minus 0.06, and minus 0.08. Okay, so we've got positive and negative displacement. So this line here is the kinetic energy. So when we have the maximum kinetic energy, we would have the minimum value of elastic potential energy, and that's going to be my green line. Okay. When you've got 0 kinetic energy, we're going to have our maximum value. Okay. And effectively, I've seen this graph come up, or this kind of graph come up in a few kind of similar exam things. And basically, the value of the green line that I'm doing for the elastic potential energy plus the value of the black line must total the line here for the total energy. Now, I would say that we've got like a little bit of a square there, so I'm going to put a little bit of a square here. That's about half a square. We then have 1 square. We have 2 squares. We then have about 3 and a bit. We then have 4 squares, so I'm going up. Is that right? No, so we go down 5, so I'm going up 5. And we basically get a shape that looks like this. Okay, so yeah, it's like an x kind of squared relationship. We'd have the same on the other side. So I'm just going to kind of plot my points here fairly quickly. It doesn't take too long to do, but it's worth just spending a little bit of time setting everything up when you start doing it. Okay, so this is the kind of shape that we have. So it's the shape of a quadratic graph. Is that because the elastic potential is proportional to x squared? Yeah, I mean, you could say that I guess the velocities, yeah, I guess, well, we'll come on to that in a sec. So let me just put in this line. I'm going to see if I can draw this freehand. Okay, so that's the shape of line that we'd have for the elastic potential energy. I think that is an awesome curve. And basically what we have, elastic potential is proportional to x squared. That's pretty smooth, I think, isn't it? It's not too bad. Of course, I would say that if you're doing this in an exam, have your pencil first. So if you do mess it up, you can at least kind of rub it out and actually, you know, put in a better line. They're not going to look for perfection. They just want to see that you've got approximately the right thing. And I think that's why plotting these points here, you know, if you look that that's down 1 square, we go up 1 square here, putting in those little crosses, or you could even just do them in pencil as like these kind of construction lines. That will help you get that smoother line. And effectively what we have is the energy is going to be proportional to maybe, thinking about the kinetic energy, EK, is going to be proportional to V squared. And of course, that velocity is going to be related to the displacement. And of course, if you're in year 13, this is the kind of time I think you need to be really familiar with your data books, so you know exactly which formulas are given to you, and that formula that links like the velocity to the displacement or the acceleration. Okay, so that question there, I reckon you could answer that question with your current year 12 or year even GCSE knowledge, because it sort of takes you through step by step. And this, I think, is an important graph. Now, this graph here looks at the relationship between the kinetic energy and the elastic potential energy and the total energy for an oscillating system. Now, that was a simple system which was oscillating side to side. The other type you might have is a vertical spring mass system, but that's a little bit more complicated because we have changing kinetic energy, which is probably going to look the same. We also have a changing gravitational potential energy and a changing elastic potential energy, because we just have one spring that's getting longer and shorter. Is the area under the curve equal to anything, or does that not matter? That's a good question. Does the area under that curve equal anything? I don't know. I should know that. It will probably have a meaning, but I don't know off the top of my head. Sorry about that, Lucy. I'm afraid I'd rather sort of say I don't know than give you an answer. But I don't think it's an area. I don't think it's an area that represents anything that you have to know about for A level. Bramble's got a really good question. In the exam for graphs and tangents, should they be done in pencil, then gone over in pen, or just left in pencil? I reckon you should, if you're doing a graph or a tangent, my advice would be to do it in pencil first of all. And when you know that you've got the right shape or the right tangent, because it is difficult to draw a tangent, or maybe you've got like a line of best fit or worst acceptable line of best fit, I would say do it in pencil first of all, and then go over in a biro or a pen afterwards, just to make sure that you know that it's going to get scanned in. The danger is that if you do a line in pencil, say for example there's a tangent that you wanted to this line here, and you kind of drew it in pencil like that, there's a danger that when it gets scanned in, because basically nobody's actually physically looking at your exam paper, all that happens is that paper gets scanned in. Anything outside the lines isn't guaranteed to be scanned in, and it won't necessarily pick up a light thing like that. So I would say, if you've got a biro, it's less likely to smudge, and go over at the end in pen, but go over your pencil lines. And that means you know that if you had made a mistake, you could have rubbed it out, and also that you do know that it's in the darkest pen possible, and that's obviously using black. Okay, hopefully that helps. I think we're kind of pretty much done there. So there we go. And of course, if you haven't already seen, you know that with my daily workout books, I do have work solutions on my website. I've got the answers in the back, so you can see like the 13th of September, which is the questions we've done tonight. This is what it looks like. It just says to the left, to the left. There's like some kind of song there. It decreases to the right, and then you've got like the kind of the small graph there. But I also have downloadable work solutions to all of my questions. So this is exactly what you download. So if you wanted to, and you've got the books, then this is kind of the thing you'd see. And there's also a video where I explain it in a little bit more detail. Right. Does anybody have any quick questions for the last couple of minutes before we get on to, I guess for me, preparing for the next day's live stream? I'm going to be live pretty much every day at 8 o'clock. I guess as we go closer to the exam season, I know that lots of A-level people are watching this. If there will be times when, if we're delayed a bit, then, or sorry, not if we're delayed, but if there's deep questions that people are asking, if people want to ask extra things, I can do some of that in the chat, kind of related to that content. And that means we can go beyond 8:30. The other thing I was saying earlier in the stream is that I'll probably be doing some like last minute panic revision sessions I was thinking maybe 3 hours on like a Saturday morning or a Sunday morning. Yeah. And basically those things will probably be done on Zoom, so there's less people, but that means you can actually watch it afterwards. You can ask better questions and so on. Okay. Right. So Joe says, would I suggest bringing a pair of compasses to the physics exam? I reckon the things that people forget are a protractor and a compass. Okay, bring a compass in case there's something where you need to sketch a circular thing. Yeah, bring a compass or a pair of compasses. Bring a nice new protractor that's not scratched and damaged. Bring a 30 centimetre clear ruler, and that's the kind of thing that, you know, that will just make any diagrams easier. Okay, right. Somebody says, okay, so some good questions. Ben says he had a materials exam on Friday. Ben, hope it all went all right. Videos really helped, thank you. Can I make some in each part of the spec, like amorphous and things? Anamorphous. I don't know if I'll have them done in time for this year. Okay, sorry about that. What's the best way to revise paper 1 right now for AQA A-level if you've done all the PMT questions? Okay, so if you've done all the PMT questions, well, basically, you just want to make sure, and maybe like just write down like a grid of have you done every single one of the OCR, or sorry, if you've done the AQA stuff, what's the best way to revise for paper 1? On PMT, there are obviously all the multiple choice questions where I've got work solutions for all of them for AQA. That's definitely useful to look at. Make sure you've done every single AQA past paper for the current spec, and then I would say go and look back at the previous spec and just work back in time order. So like do like 2015, then 2014, then 2013, then 2012. Just past paper after past paper. Right. What's the best way to organise your day to help you revise? Light Argent, I think the things that you want to do are to reduce friction. So that means spend a bit of time printing out all the papers so you've just got them all kind of stacked up, ready to go. So you're not doing a paper then having to find somewhere to like print it out. I think keep a record of what you're doing. So, you know, you've done like the 2019 paper, you've done the 2018 paper. So just keeping a tally of what you've actually done. But also, in terms of organising your day, I reckon trying to do things at the same time each day just gets you into the system so that you know, you might have tea at a certain time, and then 8 o'clock till 9:30 is when you're doing past papers, and it's just the same thing every day, and it's a bit boring, but it's only really for a month or two. I'm finding that because I'm doing these live streams at the same time every day, I've got my setup really well kind of sorted out now. I've got everything now printed out for the rest of this week. I've got stuff on the website organised, and I know because I'm doing the same thing every day pretty much, that really helps just remove friction and just get into that routine of doing things. How to deal with exam stress? That's a really good question. There's not an easy answer. I think that, again, in terms of exam stress, hopefully you've done some practice exams at school, so you know exactly which room you're going to, you know how to get to school so you're not going to be late. You know you've definitely got all the equipment and you've got spare equipment so that if you can't find your protractor or you can't find your compass on the morning of the exam, you've got a spare one that you might just have in your bag that just sits there just in case. And also, I think, and this kind of helps Lucy as well possibly, is that the way to kind of feel more confident or to work a little bit quicker is just to do as many past paper questions as possible, and just like the more questions you do, the more confident you'll be, because as you do stuff in the future, you'll recognise bits from previous kind of exam papers, you'll recognise similar styles of questions, because not everything's going to be completely new this year. But also, the more you do, the quicker you get at things, and that means the time pressure is not so bad. Time is a big thing. So yeah, you're not alone, Lucy. I would say as well, you've got to get ruthless when you're doing a past paper, where if there's a question that you think, I know the answer, but it's just taking me too long to get to, you've just got to leave it and come back to it later. Get the easy marks first of all, because there's nothing worse than spending 10 minutes on a difficult question, which is only worth 4 marks. You've got to get ruthless about going, okay, that's taking a long time, I'm going to come back to that later, rather than sort of getting every question 100% complete. So you can chop and change around the whole exam paper. You know that there's going to be some that are easy, like they take 30 seconds. Other ones, You might know the answer, but it might take you 10 minutes to get the answer, and that's 10 minutes you're not working on the easier questions later on. Hopefully that helps. And also, the last thing I'm going to say today is that any tips for 6 markers? Yeah, I reckon if you go into every 6 marker desperately trying to get 6 out of 6, then that's difficult. And mentally you're thinking, well, I need to get up to 100%. If you look at the grade boundaries, often you can get a grade A or an A star with like 60% in the exam. And so really, if you went into that 6 marker thinking, I'm going to aim for 4 marks, and if you get 4 marks out of 6, that's still like a grade A or an A star kind of answer. So don't feel that you have to get 6, because I think sometimes people feel they have to get all the marks in a 6 marker, and that kind of puts them off starting. Just remember there'll be a couple of easy marks in it that are just like stating obvious things or some definitions. And actually to go from 2 marks to 4 marks isn't such a big leap. So don't feel you have to get it perfect, just get it good enough to get 4 out of 6. And that might be a good way to kind of start those questions. Okay, are bullet points allowed for wordy questions, Ben? Yes, they are, provided they're in the logical order and you spelt key scientific terms correctly. And I think bullet points help the people answering and marking your work to know that you've actually answered it and you've understood the physics. Okay, right, I'm afraid I'm going to have to leave it there. Some great questions though, but I will be answering more stuff in the sort of coming live streams. But yeah, basically, thank you so much everybody. I'll be back again tomorrow night from 7:30 for GCSE and then from 8 o'clock for A-Level. If you haven't already done so, head over to A-Level Physics Online and spend half an hour just clicking on links, exploring, looking at the videos out there, because there's like hundreds and hundreds of videos that cover the whole A-Level physics course. There's lots of extra bits sort of hidden away on the site, so just spend half an hour looking at the site, alevelphysicsonline.com. There's a lot there to help you, and if you're year 13, it's still not too late. You can buy a premium plan, and that means you get access to everything between now and your exams, so you can go in feeling confident. Thanks so much everybody, and I'll see all of you again tomorrow. Thank you.